Unmute. Hello. It says I'm live. I hope I'm live. There you go. AussyCC is live. I hope it's working. Yes, it is. Good. Nice. Well, I'll start by saying what happened through the week. It says it's live, so I presume it all works. Last week I had some mute problems where it didn't work and it wasn't very good. So I'm trying to do it differently this week, where I hope that I don't have any dramas like last week. I had to edit out like 12 or 14 minutes or something like that just to try and make it work good. So that's good. So g'day Joe Bro, he said it's all right. Yay. Good. All right. Well, share screen. Some cool things happened this week. Where do I go here? Hang on, just got to remember to get into it. Yeah, I just heard smoke, so lives. Show the entire screen. That'll make it easier. Allow. All right, you can see all of this stuff now that I'm sharing. Good. Now I'll do this. How rad's this? I love it. I love it. Look at that. Oh, wow. I saw that photo and I just thought, it's on. Bloody oath it is. Yep, it's just what a keeper. And you can see all the different cells in it. This is the best bit about it. I've been playing around with the microscope. Oh, this isn't from me either. I'd love to claim it. But it's not. Actually, I'm going to have to show you my other microscope ones because they've turned out pretty good. I'm trying to get some cellular structure in there because, see, these stalked glandular trichomes, they're stalked capitate, and that's the glandular head on the top. They've got the cells inside of it, and you can see the actual cells. See the cell walls that make up the cells? That's so cool. And in there, look at all the bubbles. So that's all the different oils and constituents and phenols and flavonoids and terpenes, all the yummy stuff that we want is in there. It's also stored in the stalk too, but you can see it all now with all the little bubbles. And look, it's just, nice photo. This is a study that was done to prove that if you want to get anti-inflammation properties out of your cannabinoids, that THC alone doesn't do it. And we've kind of already knew that, but it's scientists, that don't have cannabis experience. They just don't know these things. So this is a test to prove that. Yeah, so if you want anti-inflammatory properties, don't expect THC to do it by itself. You've got to add your CBD, which is your RSO oil, which is what we all know to bring down your anti-inflammatories. Hey, hello. What else is there? Oh, yeah, in the States, because this stream goes mostly to the States. This shows, look how the progress that you guys made in legalization. So this is an updated map to show that where cannabis is legal in the USA at the moment. And that's bloody nearly everywhere. I feel sorry. Look at the middle. I feel sorry for you. And down on the southern right-hand side there, and up in the WI region, the winning region, Wisconsin. No, it's not. Sorry, I'm a bit bent. Anyway, next one. I found this interesting because this is just another thing to add to the, the pool of new virus things they've found, and they reckon lettuce chlorosis virus is a new cannabis thing that infects our plants. And what it does, it shows early signs of stunted growth and chlorosis. So down the bottom, it includes yellowing, rolling of the leaves, and brittle leaves. So yes, a lettuce chlorosis. How the hell do they name that? Anyway, that's something that's new I found this week. And this is pretty interesting too. Look, Oregon has banned synthetic cannabinoids. Government is putting out shit crap. Want to try and chop a tail off because CBD is... Anyway, so Oregon's gone and been the first state in the States to synthetically ban the cannabinoids. So beginning 1st of July in 2023, next year, they can't have them. So all this government effort to try and produce them and get rid of the plant sucked in. Yep, Oregon, props to them. I'm just not going to read all that. But that's really, really good. Some benefits of urban trees. I like this because it shows that our cannabis plants are very needed in society. So on the bottom left, so it filters out all the air pollution. Yes, it does. It cools the environment. So 2 to 4 degrees Fahrenheit, 1 to 3 degrees Celsius, it changes it because of all those all the jungle that they've gone and poured concrete, and the ground can't even breathe anymore. So it needs to transpire through the blooming plants that we plant. It reduces it improves air quality, reduces problems. It's good for bees and birds. People like to look at them and walk. Flooding, bloody money. Reduces stress. It's very good. Oh, and check this out. How's that? This is what my commiserations go out to the Japanese Prime Minister, the ex-Prime Minister got assassinated yesterday. Sorry about that, and all the Japanese people. But this is props to you. And your rad way this is Japanese logging. So what they do, they chop it off right up there. So 10 feet or 3 meters up, they'll chop it, chink, and they'll keep the roots. This tree is 700 years old. How rad's that? 700. So just keep it going. That's just sustainability. Good on yous. Love it. All right, into the chat. Hello to a few people. G'day, Raptor. Hello, ready to hit hot fire. Sure, bro. Here you go. And the next thing, oh, look at this that I found that was really amazing. So I'm into the research and technology. So this is the future of greenhouses. This is what they're going to look like soon. Actually, hang on. You don't want to see me there. There we go. You can still hear me. Good. All right, now big screen again. Where's that one? That one. Sweet. Yeah, look at this for the future of greenhouses. This is awesome. Plays. Now it's playing. Well, it says it's freaking playing, but it's not. All right. It's working there. All right, that didn't work too good. I'm going to actually just play the proper movie file. I'll share my screen again. Share screen. Entire screen. Now, where's the movie file? Just as well I got a backup. See, I'm a bit better this week. So this is the future in greenhouses. This is bloody awesome. So you put a rail track down and just slide the covers. Look at that. Just lock them in place with a crimp lock, vice jig lock, G-clamp. But look at that. Bloody excellent. Covers it down. How easy. One man can push it along like that, or if you're old or something, you can have it on a winch system. Roller wheels. So if he's designing a greenhouse, yeah, put that into the system. A few little tracks down below. Wouldn't cost much just to put that operation in. This is a nice dialed-in system. Everything opens and closes with the switches and sunset switches, photovoltaic switches, they're called. Very, very nice. This is the future. To get the price of pounds down, people have to do this. This is the only way where LPs are going to be able to compete in the future, is through greenhouses, because you've got to use the sun. If they're using too much of the environment, I'll play it again. If they're using too much of the environment, you're going to using wasted energy. And if you put solar panels up, good, it's still going to add to the pound price. So this is a way where they can get it down from $500 a pound to down to like $100 a pound, something where a business will actually profit. It's really, really good. They're full climate controlled, not these ones that move that well. I suppose you could still implement the system. It just wouldn't, have cables, clip-ins, get to the next spot, plug it in. Might be heavier though with all the fans that you're pushing. But yeah, that's all right. Next thing, I'll stop that. But yeah, isn't that fantastic? Well, actually, this is the best bit of the technology. Go. Should be just all automated and perfect. But it'll run itself. You just need someone to come in to help to defoliate at different stages, to plant and to harvest and set up. Nice work, farmers. All right, Now, the next thing, I want to talk about this week's my lectures. So in my lectures this week, we went through in the plant physiology class. I'll just share that screen. Oh, hell. I'm just going to tie a screen again. I hope it seems to be working all right. All right, let's go through these slides. All right, down to questions straight away. So the topics that we're going to talk on, that I'm going to discuss, is transpiration. I can't remember the other two that we went through. But anyway, it's a lot of water action in plants. So this is the importance of water. So I'm not going to read it. I'm going to skim through it again because I want this just to be a summary. This isn't a teaching thing. I'm just showing you what I got through, and I'll stop on the important bits and just tell you those that relate to the cannabis. So water's a solvent. Yeah, good. Yeah, it's very important because it takes nutrients, minerals, and stuff like that, hormones, all around to the plants. And without this transportation process, the plants wouldn't be able to function because they're stationary. They can't feed ourselves like we water ourselves. We throw water down our throat. They can't do that. Next one. That's how to do it. Oh, yeah. When the cells go turgid, when they get inflated with water, that's how they elongate. Properties. Water's a fantastic thermal insulator, and one of the ways one of the ways that you can use it in frost is as a frost barrier. So if you put it around the bottom, anyway, in the middle, this property is used by citrus growers. They put a light spray of water which forms ice, and the latent heat fusion helps protect the crop from serious damage. So you can also put bottles or jugs around the base of it, and that will absorb the water, the temperature, into the water before it goes into the stem of the plant. Water movement. This is a bit technical. These are the tonicities that you have in a cell. So if it's flaccid, it's full of water. If it's turgid, flaccid's empty, it's got no water in it, and turgid is full of water, and then isotonic on the right is when it's at equal pressure. And that's why if there's salts, I hope it's got diagrams. Yeah, I'm not going to go into that, actually. Good. The water potential, there's a lecture. Yeah, the diffusion pressure deficit is equal to the osmotic pressure in the plant minus the turgor pressure in the cell. I'm just going to go off this. This is pretty, and that's how you get the whole water potential in it. You got to add up the solute potential and the pressure potential inside the plant. So the solute is inside the liquid, and the pressure is the amount of pressure exerted. Gravity and matrix is due to the soil or medium that it's in. So you don't really use gravity and matrix because our plants aren't very high. So it's only solute potential and pressure potential, and you can work out the water potential. This goes into a little bit. So solute is in your solution, and that's what adds to the pressure. Because if you've got a high amounts of salts, it's going to put more pressure in it. And the pressure is, well, we know what pressure is. It's just the amount of mechanical pressure exerted onto a cell. Gravity, that's for big trees, and matrix is in your substrates, which isn't really to do. Anyway, next things. For water to move through the plant, this is in the root hairs. So this is a sliced section of a root hair, and see on the left-hand side, there's some root hairs, and there's 3 ways that the water or your liquids can transport into the plant. There's the symplastic way, the apoplastic way, and through the transmembrane pathways, the 3 pathways, and these lines show it. And then it gets to the Caspian strip in here, and that's like a big blocking area, and it's really hard to get through that. So when it comes in through the transmembrane way, it jumps into the cell. And when it goes into the cells, it goes through this little tiny cell opening called a plasmodesmata. Actually, it might show it up here. Cool, it does. These are the 3 different ways it just briefly explains. So see, these are the in the plasmodesmata. That's the little cell linkages for the cells to communicate And as long as they don't have any callose on top of it, which is the little formations they get to block the cell pathways. So you can get extra formations of that stuff, which stops them as well. So that was the apoplast pathway, the transmembrane, and the symplastic pathway. What's that Caspian strip? Good. Questions? Do you want any? What's the following? A cell, when placed in a solution, gets plasmolyzed. What is the largest present? No, that's a bit hard. When a cell's fully turgid, which one of the following? 0. That's hard. When a cell becomes turgid. No, next. Types of transpiration. So there's 3 types. So there's stomatal, the cuticular, and lenticular. 3 ways that it can transpire, which means it can remove the vapors out through these pores. So that's the 3 different types. So on the left, lenticular. So it's 0.1% of water losses through the lenticels. So they're little tiny pores in the stems. And I'm yet to still see some in cannabis. So yes, but I've been looking pretty hard. There's diagrams up here of what they look like. And the cuticles, that's in the waxy cuticles or the epidermal layers on the outside. So that stuff can, secrete through that. And they didn't put near this hydrothodes. So that's actually, we've got hydrothodes in our cannabis too. And it does actually, water goes through it through butation. And stomata, you know about stomata. So it's 90% of the water is lost through the stomata. And here's the lenticels. So when I'm zooming in, I'm always looking for these little openings in the plants. So this is just the cells there and the cell walls you can see represented in black. This is a waxy cuticle layer on top. So it depends, different plants. If you've got it in a area where it's very drought ridden or stuff like that, the plant puts a waxy cuticle on top and becomes shiny. What that does, that recesses your stomatas. So yeah, Mother Nature really helps, but it can be bad sometimes too. But that's anyway another way for breathe. And we know about the stomatas through the little inlets. My voice is starting to go again. Fuck it. Lenticular transpiration. Yeah. Lenticels are in the bark, yeah, on the outside. Yeah, good. Significance. This is why it's good. And so on the left, it creates it's a suction force, it creates a suction force that helps the sap to go up in the plant, which opposes gravity. It affects the DPD promotion. It affects the absorption of water in roots. Yes. So if you don't have it going through, you're not going to the minerals and nutrients aren't going to get into the plant. Helps with evaporation and cooling of the plant. Yeah. So it's very important in summer. So that's why when plants get too dry, they wilt too fast because they're just powering out. It plays a role in translocation of food. Yep, needs to get covered in nutrients. Maintains temperature. It brings openings and closings of stomata. So its disadvantages. It consumes energy. When the rate of transpiration is high and the soil deficits, the water is internal, it leads to wilting. Oh yeah, it can lead to wilting from transpiration. It causes the death of millions of plants each year from this factor. So you put drought resistance into the plant. Anyway, we're not talking about that. Shan't slides. So the rate of transpiration is effective with temperature. So as temperature goes up, it transpires. So see, if you've got no temperature, you've got no action, regardless if your lights are on. So temperature does play a big factor. Humidity. Here you go, VPD heads. Check this out. So if you've got a very high VPD here, your plant won't transpire. See that? Yeah. So that's why I always never go over 65% humidity, which is in here. So at least that's for fungal growth and for this reason. I want my plant to suck up all the nutrients as fast as possible and get them to process them and keep it all functioning and flowing. Anyway, next one. Some external factors. Well, yeah, these are the external factors related to transpiration. So you've got atmospheric humidity, the temperature, the wind velocity. More wind increases it fast. If you want your plant to transpire more, put more wind around it. Like the leaves should always be nervous when they're looking at it. The light will, in dark times, it won't transpire because the stomata is closed. CO2 levels drop too low, its stomata closes. too high, it does the same. I'm going to get a POTOMETER. That's I'd like to when I can afford it one day, but that's going to allow stomatal conductance tests, so I can do these tests and prove these things in cannabis too. And the last thing, available soil water. The rate of transpiration will decrease if there is not enough water in the soil. So that's why these people that do trickle feeding and stuff like that, that's why it helps with speedy growth. So that's the wind. And you can go too much wind. I'm going to have a drink here. You can go in too much wind, and that's when the plants don't like it. That's called strigolomorphogenesis. There you go. That's when a plant is shaped like the wind, like on the beach. Light. Yeah, well, too little light. Of course, it's not going to transpire because it's not photosynthesizing, because you need that. That's the pumping action. And the CO2, yep, covered that. It's too low. It's going to close up the stomata, which is not going to transpire. Available soil water. So if it's too low, not going to transpire either. You want the rate to be nice and equal and high, because if there's pressure, it's got to exchange something. So if the roots have no pressure, if there's no water outside to exchange in, if the pressure outside is lower, it can't exchange it and suck it in. So that's why you've got to have available water. Anti-transparent. These are things that stop it transpiring. So if you put an anti-transparent in, that's what it does. So the internal factors is stomata, and what's this middle one? Number 2. The sunken, thick cuticles, leaves, high osmotic pressure in the leaves, such as gums, mucin. That's not really related to cannabis. Other factors, spongy mesophyll, that could be from some growth. Well, here's stomatal frequency. That's right. Stomatal frequency is the amount of stomata that you got on a 1 square inch of your leaf tissue, and it's counted. That's how it's counted. And here, if you got more of them, it's going to transpire more. But if you are into polyploids, like I am, they are bigger stomata, and their stomatal frequency is actually lower because their stomata size is massive. They're 2 to 3 times the size of normal diploids, because I'm measuring mine to prove that fact at the moment. So I have to do a shitload of measurements. So that's something that could be played into this graph too. And they're not really much related. Here's the function of the stomata. So in the middle, they got these kidney-shaped guard cells, they're called. And when they have water going into them, they swell, and that's when they go turgid, and that's when they'll start and open. And what happens is they got these cells in it. See the little ribs around it? They're called the radial mycelations. And when they swell with water, that's when it starts to open and it elongates like that. And when it closes, it'll be like on the left, when it's got no water in it and it's flaccid and it's just closed. So this is turgid in the middle. And they got little tiny bits of, see the green things? They got little chlorophyll in them too. It's pretty cool, but they don't have many. That's because they are a cell, so they do have all the organelles. What's all this? Stomatal 5 categories to stomatal movement. Autonomous, passive. It's just saying it can open from different ways. It's the ways that it's moved is from light, is from water, is from what's that one? Rhythmic pomp. It's from circadian rhythm. Because plants they keep a pretty cool circadian rhythm. And if you try and turn them on when they're in different stages, like they will respond like in a circadian rhythm. It's pretty cool. Is that the last slide? Oh no. Types of theories of the guard cells. I'll just explain it. The potassium goes in, water goes in, that's it. And at night they shut. It's in the middle, they got a little slanty looking eye, they're closed. I'm not going to go into the theories, but turgidity, good on it. That's how it works. So abscisic acid, that's another hormone, basic hormone that stops like if kombucha releases the gases, vinegar releases gases, and that's abscisic acid has it in it. So they will shut stomata. So if you want to do that, ferment kombucha, for instance, in your tent, you're going to get this sort of action. They're going to struggle because it leads to a calcium influx, and then that process is downline, which leads to the calcium influx, which leads to a potassium ions to come into the cells with water, which makes them change their state. And during the day, the stomata are open. During the night, they're closed. It's a little bit how they do it. Push pumps out. Yep. And blue light changed their reaction. So if you want to put a blue light onto the stomata, it's supposed to excite the xanthan, which is a pigment, and that has the signaling cascade here, which will open stomata. Weighing method. Look how cool this is. You can weigh your plant to see how much, because I study online in India, so they teach you all the old school methods. So if you haven't got technology, you can do it as well. And then they'll show you the new school methods, which is usually the USA folk, which is how they're doing it. And yeah, I like, because I'm not very rich, so I like the old school methods, so I can still do all my research and obtain results. And this is one way. So you put your plant on a set of scales and you'll cover the pot or your substrate with a bag so it's not going to release any moisture, and then you'll weigh the difference and leave it there sitting there for 8 hours, or for a growth cycle. Weigh it at the start of the growth cycle, at the end, and see what water has exchanged out through these pores, proving that that has lost through transpiration. And this is another way to do it in the lab. So I use calcium chloride, and that's a powder. So you just weigh the powder difference. You'd have air coming in here, have that go through it, so it pick up the moisture and just weigh the difference. Here's your POTOMETER, these rad stomatal conductance things. You clip on the leaves. They're like a little clip thing, and it just gives you a reading through a little USB thing. This is the old school way. How's that? So you can set it up with an air bubble and a test tube and stuff. So you cut the plant, you put it in there, and it's still going to drink. So this air bubble in here is going to move up the scale and deflect when it's, changing its state in the leaves, so that it's moved. So it'll probably move up a bit because it should have taken some water from transpiration. So it's the analog version of making your POTOMETER. There's some questions. They're probably a bit challenging. The meaning of sap. This is pretty cool. The sap is dilute solution of water and mineral ions absorbed from soil, which moves upwards from roots to various parts of the plant. The process of translocation of sap from roots to the top of the plant against the force of gravity is called conduction or translocation of water, which is pretty much what we just went fully through. And I wonder if I can pause it here. I'm going to show you right now. Actually, I'm going to look for it. Oh, no, stuff it. Just get straight back to it. Sorry about that. Now I don't know where I was. I was here. Good. I was going to show you what's the constituents of the sap are. There's about like 18 different things inside of the sap, what it makes up of. And I've got a chart of that. But I'm showing what I studied this week. I'm not getting off topic. Sorry. So this is the cohesion tension theory, which is how the plants work. So it's from the water molecules. When they leave the plant through the atmosphere, that's created a force, and that force has got to be filled. So that's a pulling force, which is the cohesion bit. So it'll bond and pull moisture or something in that's around the roots. Because they put out the exudates, they would have already sourced their elements that they require through the microbes. They speak with their quorum sensing, and they would have got what they wanted. So when this evaporation, when the transpiration happens, it's going to create the pressure, which is going to suck in from the soil. That's basically explaining that bit. You can test that, of course, by setting it up a similar way, by putting a test tube down there in the bottom filled with water connected to your plant, and you can see the difference with the stem. I haven't done it, but it'd be pretty cool to see what's root pressure is going on. Root pressure serves, in modern times, root pressure serves as the starter and the transpiration is the motor. So without the transpiration, there's no force there to actually suck the roots, the stuff up like we're saying, which is the starter. So the combined effects help tall plants like those big ass redwoods get to the tops. So that's why those redwoods couldn't evolve in high humidity or in VPD conditions, because they wouldn't transpire enough. Root pressure theory. Root pressure can transport water and dissolve minerals, nutrients from the roots and the xylem to the tops of the short plants. See, we don't have to worry about this sort of stuff. Actually, yes, we do. Sorry about that. I was thinking about redwoods in my head then when I said that. We definitely do. Root pressure theory is so important. But it's more so for the top plants. But still, if you have no root pressure, shit, you're not going to get any action. So what's the point in sort of watering them? So it's extremely important. And I like this for point 9. Salt burning. Burning of the leaf tips is due to evaporation of the solute-rich exudates of guttation, meaning that we've got hydrothodes in the tips of the leaves, and when they respire, little water droplets go out through it. And that's what this is saying. But in cannabis, it does show up. It doesn't show up that each little segment of leaf tip is called a margin, and that suggests it shows up on each margin, where in cannabis it shows up on the edge of the leaf point itself, the tip. Oh, rad, guttation. Here you go. We'll be into the hydrothodes. So when there is high soil moisture, water will enter the roots, yes, because of the... I'll speed it up a bit. Water goes out through the leaves, through the leaf tips, when there's the guttation process is happening. So you might think, oh, look, it looks like dew in the morning, but it's not. It's guttation, and I've seen it. Here you go, rad. I'm going to try and zoom in for you. So see on the leaf tips there, there's water coming out. So you'll see it with cannabis. I've seen it, but I didn't get a bloody photo, and I've only seen it once. And that's what it looked like up the top. Solid leaf tips, solid water droplets coming out of the tips, and that's called on the left guttation. And that's from excessive moisture coming up through the root pressure, which puts the xylem zap out there. So if you taste it, the phloem zap is a lot more mineral rich. It's an orangey sort of color, and it's got sweetness to it, where the xylem zap is more so water, and it's unidirectional. It flows only in one direction from the roots to the tip, where the phloem flows both directions. It's bidirectional, not a unidirectional flow. I'm not going to read all that, because that's sort of what guttation is. Guttation fluid may contain various organic and inorganic compounds. Like catalase, amylase, peroxidase. They're really good enzymes that are really beneficial for plants and humans. They break down all of the bad things. Amylase is for starch. It's peroxidase is the free radicals. Peroxide. It's really, really good. Hydrothodes, yay. So this is another opening in the plant. So for those people that think, oh, it's only the stomata, no, there is this. There's the lenticels, nectithodes. We don't have the nectithodes. And there's through the cuticles, the epidermal layers. So foliar spraying does work, and that's how it enters into the plants. So hydrothodes, they're made up of rupa cells. Yeah, good. No more they're mainly just to breathe. That's what they are down the bottom. Yeah, open water they're like a stoma pore. A stoma is one, and stomata is plural for more than one stomata. So if you're single, it's a stoma. Hydrothodes and modified stomatas. There you go. What's this saying? There's 2 types of hydrothodes in plants: an epithem ones and active ones. Mineral absorption. Oh, okay. Well, this is through the smallest motor in the world, through the proton pump. I covered that in that video not long ago. World's smallest motor that functions. It's so rad. It's got a rotor and a stator on it, and it transforms these protons, the hydrogen plus, through, and that gives it energy. So it reacts with something and forms the ATP, the currency of the cell. What's it say? Yeah. Oh, and this is interesting. Look, this shows technology. So this shows that this is the basic nutrients, CHNO, which makes up 96% of a plant. The nutrient requirements is from 3 elements, carbon, hydrogen, and oxygen, that all come from the atmosphere. Then in the macros, well, there's bloody 7. They forgot, well, there's nitrogen, phosphorus, potassium, calcium, calmag, sulfur, and silicon. So this shows technology. So it just shows how science evolves, and if you stick with it, you'll see the evolvements and how technology can prove different theories correct and incorrect as well. So this, back in the 60s, there was 16 essential elements. In the 70s, they added one more, nickel, to the micro elements. And then a bit later, I'm picturing all this, in the 90s and the 1000s, they added nickel, then they added 2 more, now to be up to 19 essential elements. Yeah, anyway. In a plant, nitrogen converts to amino acids. It's a backbone, yeah, of everything. It's really, really important. What's this? Oh, that's right. This went into a brief description now of the macronutrients. So the macronutrients in the plant is the 7 elements. Then you go into the 10 micronutrients afterwards. Please don't ask me to name them. It's too early. Well, I can try if you want, but I'm not reading chat, so it's sucked in. I can't even see what you're saying. Yeah, so this is what that's going to briefly touch on, these 6. So yeah, it's pretty important. It's good for amino acids, and they're the backbones. It's good for chlorophyll, magnesium. You know all about nitrogen. It just fades. It's a general fading of the yellow on the whole of the overall plant. And like, yeah, there's some technical stuff, how the TCA system, well, it's a bit too technical. This is a root tip, and this shows you how the mycorrhiza work with it. So we're into phosphorus now. So they're really good at helping phosphorus get into the plant, mycorrhiza fungi. So there's 2 types. There's your active and your sequescent. Well, it's an internal and an external. There's a arbucular mycorrhiza. That's too early. I'm not going to get into that. This is confusing me. But this is just showing how the phosphorus can get into the root tip, just showing its different pathways, how it can get in with the addition of having mycorrhiza, which is really good. Phosphorus is also important for your bilipid layer. This forms the outside of the cells. So this is what a cell wall looks like. And then that's how it keeps separation. And then these are the receptors. So that's how you engage a receptor on the outside of the cell wall. It makes the right thing to turn it on, and then it'll store stuff up in here. And then once it's turned on, chink, it'll release this stuff at the other end. Types of phosphorus containing cell membranes. That's a bit technical. ATP. That's the adenine triphosphate, is the currency. It's like the sugar of the cell. That's what it uses to produce the energy. Same in us too. And phosphorus is a really good backbone of it. See, it's showing there in its carbon chain and its molecular chain. There's no carbon in that, but it's one of the compounds in it. Secondary phosphorylation. Phosphorylation is what I explained before about how the proton goes in and exchanges in through the world's smallest motor. This is just the different genes engaging. So cyclin in there, cyclin-dependent kinase, CDK, ethylene, subscription factor, Anthocyanin accumulates due to phosphorus deficiencies. This is new. This is something that I'll be researching. So I'm sharing all my shit with you now so you can research and give me your experiments as well. So they're suggesting here that phosphorus deficiency brings out the anthocyanins. So cool. Let's try it. Let's make it hell deficient at the end and see if it bloody works. It's another thing, trigger, because I've triggered it. I use my temperature to trigger it because I know if you get it under 18 Celsius or what's the conversion? 60, is it 60? Yeah, 60 Fahrenheit for 5 days at 4 hours minimum a night from day 40 to day 60, you will trigger and grow your anthocyanins on your calyxes 1 millimeter per 4-hour night. And that's what I do to engage mine. But phosphorus, they suggest. Potassium does a few cool things. I'll read them. Helps with photosynthesis, enzymes, phloem exports, cell elongation, protein synthesis, water, transportation, and stress factors. This is what potassium deficiency looks like. There you can see it there. So it's got it's got to have the greyish, the burnt tips on the end. Otherwise, it'll be sort of nearly magnesium. So if they're going, because magnesium won't burn at the end, where potassium will. There's a better one. So it sits a bit darker on this leaf here. It sits darker on there. There you go. Add some potassium. Sulfur now. Sulfur's really good for amino acids. See, it's in their chain as well. I can say carbon chain because there's carbon in there now. Helps with your B vitamins too. It's one of the compounds inside that. So if you don't have sulfur, this compound can't link up and form. So by having it, it will enable you to have the more B vitamins formed, which is so important. V vitamins, you want them a lot for your microbes. They're really going to help shitloads and improve their health, which is going to in turn improve your plant's health. The function of sulfur in plants, sulfur lipids, glutathione, and your aminos. Sulfur deficiency is long, streaky looking line things. Calcium now. Calcium's really good for building thick cell walls, because cell walls have the pectin in it. So calcium reacts with pectin, and the outcome of reaction is it hardens, and that's what gives you your cell walls. So if you don't have that, this is a deficiency. Starting. So on the left here, it's good. Middle, it's starting to get deficient. And on the right here, it's broken already apart. And this is what it looks like. So cell walls break. So they're twisting and curving. They're fully flaccid. They've lost everything. All the vacuole pressure is gone, everything, and they're just twisted and shit. So it's a good sign of calcium. Magnesium. Magnesium's good for. Yeah, there you go. Magnesium is a structural compound of chlorophyll. So if your leaves if they're starting to yellow, there's a sign magnesium is leaving your leaves. That's how it functions. See in here so this is inside of your pigments, your photosynthesis pigments. So it builds nitrogen to build one of the molecules, and magnesium is the inside of it. So very important. Without that, this molecule wouldn't be able to be formed, which is your yellow molecule. Foreign ring shown in red. Oh yeah, but that's that's how it works. So yeah, see on the leaf tips there on the right, there's no browning. It's just staying yellow. So if it was potassium, that's where it would be browning. Nitrogen metabolization. Yeah, what can I tell you here? Well, there's two forms of nitrogen in the plant that the plants can uptake without being broken down. And that's your NO3, which is your nitrates, and your NH4, which is your ammonium. And so your nitrates come in, they're going to be broken down, and then they got broken back up. And then this is into the cell. The cell does this, and then it's stored and then processed. So yes, that's what else can I tell you about? No, sticking to the topic. We're into sulfur. No, this doesn't look like sulfur. This is, what's this showing? This is showing the backbone of, sorry, don't know what I was up to, because I was getting off topic, man. See, we're talking about nitrogen now. Okay. What's this showing? NH3. Yep. Well, there's some nitrate there with ATP mixes, and it forms the glutamine. So that's energy. So it mixes with that. This is just the process that's telling you, okay, how it does it. Mixes with the urea. That's another form. Nitrogen breaks it. Okay, next. It's too technical. Calcium. Calcium's an immobile, one of the 5 immobile things. There's not many of them that are immobile elements. This is one of them. Whoops. Relay pump. What's on? Oh, these are a bit hard questions. The opening and closing of the guard cells is favored by sodium, potassium, magnesium, or iron. Which one? It's potassium. K+. Mycorrhiza fungi with help with the absorption of hydrogen, sodium, nitrate, or any. And in this, it said before that it helps with phosphorus, but it actually does help with any. It's really good because it can assimilate, it can take it in itself because it needs functions to do, and then it can break it down inside of the plant as well. When it's inside of the plant, it's endo, and outside of the plant, it's ecto, because end means in. And then the next one, start the questions. What else? Oh, is that it? Oh, that's the end, is it? That's the end of this week's notes. Okay, sorry. What else? Back to chat. I'll say, all right, do you have any questions in chat? I think I'm getting close to this week's discussions that I want to bring up. Plants about that. So is there any, I'll put the thing in for anybody that wants to say g'day. And if you've pumped your questions out now, guys, because I'm reading chat, I'll put this back into. If you've got any questions, I'll get the link, and if anyone wants to join, they're welcome to join. And that's pretty much what I was going to discuss today. Oh, here we go. Some questions. Is that fancy word in purple pigment? Wonder if the sulfur in magnesium sulfate is enough. Magnesium, yes, well, it does. When you've got the compounds that they're called salts, when 2 compounds are added to each other, and if they're in the right form, let me pull up this chart for you. I'm not sharing screen. No. I'm going to get to this Skizbit. Hey, Skizbit. Nice question. I'm going to find that question for you, mate. I'm going to explain to you about salts and how they combine with each other. So you use magnesium sulfate. Right, let's find that. What am I looking for? I'm looking for the chart of, so I can't see the questions now at the moment because I'm looking through all my slides at the chart for the difference, where is it, microirrigation engineering, because we went through in that extensively about elements that are needed to be used to break down, because things don't work in different irrigation setups. So they show which things are mobile and which things aren't mobile with each other. I actually know where it is. I was going to go through all these. I'm just going to go through all these notes because I know you're waiting. And see, it's hard for me to find these questions, but I'll get you the answer. I wonder if you want to see all my slides too. I'd like to see what you're saying. This might take ages. It's not a thing I talk about lots because it's a technical question, but I've got the answer here for you. They show you what elements. Here it is. Fertilizer votes. Yep, it's for all right. Share screen. All right, where is it? Oh, what's wrapped up saying fungi, the internet of nature. Fungi is awesome, mate. It really is. It helps so many different ways. All right, I'll share screen again, and I'll get up to the stuff that I was talking about what elements are combined with each other. Oh, it's not working. There we go. Where's the big chart that I wanted? This one. So the compatibility of different elements in water. So you can see here you've got a low compatibility and you've got no compatibility. So, I even forgot what he's doing. Sulfur and something he's mixing it with. Shit, sorry. Damn it. Well, when two elements are combined, they're called salts, and some of them aren't compatible. C means compatible. Down the bottom here, here's the scale. LC is low compatibility, limited, and N means they don't compatible, which means when you add them together, they'll form salts. So they'll just form like a white sort of solution or a yellowy solution, or some sort of crystalline solution will form when you've added them together, and that means they're not compatible. They will clog up irrigation systems. That's why they had to extensively go into this. And I was going to try and find your sulfate with your other compound and see if it was on this chart here for you. There's a few of the charts. Solubility, seeing it's got its gram per rating of its solubility of the different. So for potassium fertilizers, these are the different ones you use, and it's got its solubility. So if it's really soluble, that's what you want. If it's like this, potassium chloride, it means it's not soluble, mate. It's not going to mix well, and you're going to get some precipitation forming. Very good chance you're going to clog up your shit, and it's not going to give you the outcome that you want. But if you use potassium sulfate, they are going to blend well and release their bonds between them aren't tight. So they might have like 2 or 3 hydrogen bonds, which are very hard to break, like water has. So I'd love to see what your question is. I'm just going to skim back, actually. And sulfur, damn it, sulfur magnesium sulfate. You can see what I'm doing. You just must be laughing. Look at this, crazy. Magnesium sulfate. Whoops. Nitrogen, magnesium sulfate. It doesn't have, this has only got the 3. Oh, no, it had more than that. Oh, well, I'm not finding it now. Sorry, I'm looking at stuff he's up. Thanks for the question, no. That was good. All right, I'm going to find this link if anyone wants to say g'day. There's the link. I'll put it in the copy into there. I'm still, yeah, you can still hear me. Sweet. Wow, it's going all right. So I'll just scroll up and see if there's any questions from a while ago. Thanks everybody for joining. Appreciate you being here and asking stuff and looking at the shit that I've got to put out. I'm interested in the technology stuff, so I really enjoy that. Even if you don't follow you. Sunshine says, not sure what that was. No, I can't see any more questions. A few more people. G'day, Weed Wars. Hello, Lene, Buttercup, Duncan Biscuits. Who else is there to say g'day to? Raptor said hello to. Ready to hit hot fire. Devon Shipwreck. Hello, Devon Shipwreck. G'day, Chur Bro. How you going, Chur Bro? Weed Wars, yep. Just been a fair bit of chat. Terrence Down Under. G'day, Terrence Down Under. Terrence Down Under, you have to check him out. He's quite up there with his fungi. If you guys are into your fungi, he's Raptor, you're into your fungi, you might like Terrence Down Under. He's got a show. He's in Australia, and he's into his fungi, mate. So Raptor is into his fungi too, Terrence. You two might like to hook up. Yeah, Devon, Shipwreck, it's going good, mate. I don't think there's any failures today. Everything's been going pretty smooth, so I can't complain. But I'll be ending this very soon, I can tell you. If there's no more questions coming through, I'm going to be pressing the end button, and I appreciate. G'day, Matthew Flick. Keep up the good work. Tried like some of your stuff. Yeah, well, I'm trying with the videos at the moment. You'll see some videos coming out soon where I put a pretty decent effort in. I'm sharing all my slides, and I'm actually, some of them take 8 to 12 hours, some of them movies to make. They're very hard, but I'm still, so please share them. That's probably about all I'm looking for. It's just some really sharing of them just to get them out, because I want to share the proper word, because I'm trying to relate it to cannabis, all this agricultural stuff, and to show the slides so it computes and sinks in for people, not just being a verbalologist. Here, I'll put this in the background while I'm talking, because you don't want to talk and look at trichomes. You've seen it enough probably. It's not playing. Because there was another question up here that was there before. I thought something come through as a question. Hey man, yeah. Duncan asks, is there any info from the Indian dude on the benefits of using biochar? Yes. Well, I don't know about the Indian dude, but biochar is really helpful for, it's like a little home for microbes. So they have to live somewhere. They got to create a home, and the biochar allows it to happen. So in how you make biochar, you get charcoal and then you activate it by soaking it in calcium chloride, and then you reduce the calcium chloride in the oven, and that's activated. That's how you make activated charcoal too. So your biochar is just got, then you inoculate it with biological organisms, and then that's biological char. Biochar. And they can house up and get their little, because microbes, they put out bioslime, so they want to create their own environments. So if they got one little hole or one little pore in the biochar, that's theirs. They can fill it up with all their biofilm, which has all of their different quorum sensing in it, and it can talk to their microbes that they like. And then the bad microbes, they put out antibiotics in it, and it repels all the other ones that they don't like. So then they can still proliferate and still function well. So biochar is really, really helpful. I'd add it to my organic blend for sure, but I try and recycle my wood chips and old biochar that I get in my organic compost that I have to buy sometimes, and yeah, that's how I do it. Hope that helps. Biochar would be a natural source of potash. Well, potash, not the biochar is the carbon bits left over afterwards. So the potash you're looking for is the ash bits, the sort of greyish matter. I don't know what it might be carbon too, but the biochar is the solid bits, and the potash stuff you're looking for that's really good and high in potash is the ashy, lighter stuff, the stuff which wouldn't hold the microbes. I'll sure check it out. What's Duncan's hemp and cannabis biochar testing at 200% better. Yeah, see, there you go. Yeah, because it helps with the microbes, and the microbes work with the roots, and that's what speaks to the plants. That's perfect. All right, everyone. I appreciate you for being here. I'm going to end it. It's been an hour. You listened to me crap on for long enough. Thanks again. I'll be here next week, and I'll go through some more slides. There's some cool stuff we're going to go through next week in my classes. My soil fertility and fertilizer and post-harvest operations. That hasn't started yet, so when that starts up, it'll be on for young and old. All right. Thanks, everyone, again. Appreciate it. See you this time next week, and check my vid I watch I'm going to release through the week. All right. I'm going to end it. Bye-bye. Happy breeding, happy growing to you. See ya.